Section 3.5, Combustion Analysis. Here what we're going to do is we're going to determine the empirical formula and the molecular formula of an organic compound. So combustion analysis is based on the following idea. There are compounds, organic compounds, that contain carbon and hydrogen, or carbon, hydrogen, and oxygen. And we can use a particular experimental technique to figure out what their formulas are from a small sample. So the idea here is that the sample is placed inside of a furnace. So if you look here at figure 3.5, it's a schematic of a combustion analysis apparatus. The sample is heated in a furnace to a high enough temperature that it reacts with a flow of oxygen gas. The oxygen reacts, it combusts the organic material, combusting it into carbon dioxide and water. So those are gases, and so the carbon dioxide and water vapor flow through this device, and some of it is absorbed, some of the water is absorbed in the middle chamber here, actually the third chamber from the left, and then some of the carbon dioxide is absorbed by the last chamber on the far right. The materials that are used to absorb the water and the carbon dioxide are not shown here, but there are many materials such as calcium sulfate that can absorb water, and there are many materials such as lithium hydroxide that can absorb carbon dioxide. So the logic is this. You weigh the sample so you know how much of the compound you have. You then combust it, and the water that is produced in the reaction is absorbed, and you weigh that. So you weigh the little disc that's shown there. Then after the water is absorbed, you weigh it again. The difference in those two masses tells you how much water was absorbed. So that essentially tells you how much water was produced in the reaction. The carbon dioxide is absorbed in the final chamber, and same thing, we weigh the disc before the reaction, we weigh it after the carbon dioxide is absorbed. The difference in those two masses tells you the mass of carbon dioxide produced in the reaction. From that information, the mass of the water and the mass of the carbon dioxide produced, we can figure out how much carbon was in the original sample from the carbon dioxide and the amount of hydrogen that was in the sample from the mass of the water. Hydrogen comes from the mass of the water, carbon comes from the mass of the carbon dioxide. And the reason for that is that since oxygen doesn't have any hydrogen or carbon in it, any hydrogen that was produced had to come from the sample. And oxygen doesn't have any carbon in it, so any carbon that was produced also had to come from the sample. Now, if you're clever about this, if you can figure out how much hydrogen and how much carbon was produced, and the sample had oxygen, well, you can take the mass of the sample and subtract the mass of the hydrogen and the mass of the carbon from the sample mass, and that will tell you how much oxygen was originally in the sample. So now you figure out the mass of all three elements in the organic material. Now, the significance of this is once you get those masses, you can use those masses to determine the chemical formula of the sample, and that's what this method is all about. We combust the sample to figure out what it is. So if you don't know what this material is and you run it through this instrument, you could very well be able to figure out what the chemical formula and identify the material at the end. So the procedure is pretty straightforward, but it is a little involved. So I'm going to go through this determination of empirical formula. So the numbers given in this example problem are, you have a sample that has 18.8 grams. That's the mass of it. So that's the mass of the carbon, the hydrogen, and the oxygen together in the sample. Now in this particular reaction, they're using glucose, C6H12O6. So we already know what the formula is, but we're going to go through the calculation anyways. After this 18.8 grams of glucose is combusted, we produce 27.6 grams of carbon dioxide and 11.3 grams of water. we can calculate the mass of carbon and hydrogen from the original 18.8 gram sample of glucose as follows. Okay, let's do the carbon first. The amount of carbon dioxide produced is 27.6 grams. The molar mass of carbon dioxide is 44.01 grams. So 1 mole of carbon dioxide weighs 44.01 grams. So if we divide the mass of the carbon dioxide by the molar mass of carbon dioxide, that will tell us how many moles of carbon dioxide were produced. In 1 mole of carbon dioxide, there is 1 mole of carbon. There's 1 mole of carbon for every mole of carbon dioxide because of the formula, CO2. So we multiply that by 1 mole of carbon per mole of carbon dioxide to determine the number of moles of carbon that was produced. That number of moles of carbon is the number of moles of carbon that came from the sample. Then, if we multiply by the molar mass of carbon, 12.01 grams, that will tell us the mass of carbon that was in the original sample. So notice what we're doing. We're taking the mass of CO2 that was produced, and from that we're calculating the mass of carbon that was in that CO2. However, that 7.53 grams of carbon that was in the CO2 is the 7.53 grams that was in the original sample, 18.8 grams of glucose. Then we do the same thing for hydrogen using water. Remember, the hydrogen goes into the water in a combustion reaction. So it says here that 11.3 grams of water was produced. So we divide by the molar mass. This is from the previous section, right? If you have mass, you divide by molar mass in order to get moles. So the first step is dividing by the molar mass of water, 18.02 grams. That gives us the moles of water produced. But now we want to know how much hydrogen is in there. In 1 water, there are 2 hydrogens. So there's 2 moles of hydrogen for every 1 mole of water. So we multiply it by 2. That gives us the moles of hydrogen that was produced. Then, what's the molar mass of hydrogen? 1.008 grams per mole. So we multiply it by the molar mass, and that tells us that there was 1.26 grams of hydrogen in the water. However, the hydrogen in the water is the hydrogen that came from the sample. So that is also equal to 1.26 grams of hydrogen in the original sample. Now we have the masses of the first 2 elements, carbon and hydrogen. We need to find the mass of oxygen because glucose has 3 elements, not 2. How do you do that? You take the total mass, that's the mass of the sample, 18.8 grams. Subtract from that the mass of the hydrogen and the mass of the carbon. So carbon is 7.53 grams, hydrogen is 1.26 grams. The difference there is 10.0 grams. So that would be the mass of the oxygen that was in the original sample. Okay? So that's how these problems work to get the masses. Water, carbon dioxide, figure out the hydrogen, figure out the carbon. Oxygen comes from the mass of the sample minus the mass of the carbon minus the mass of the hydrogen. That doesn't really answer our question. We want the chemical formula, and masses don't give us the formulas. Moles will give us the formulas. So the next step is to take the mass and convert it to moles. We have the mass of each element. We want to convert them to moles. How do you convert the mass of an element into its moles? You divide by the molar mass. So notice here in our second stage of calculations, they're taking the moles of each element and they're dividing it by their atomic masses or their molar masses to find the moles of each element. 12.01 for carbon, 1.008 for hydrogen, 16.00 for oxygen. Those are from the periodic table. Once you've got the moles, you're almost there. The moles are really a way of measuring how many there are. So just like if I said there was 6 dozen and 12 dozen and 60 dozen, that's a measure of how many you have. Same thing with moles. Here's what you do in the next step. This is related to the last problem we looked at in the previous section. You divide the moles of each element by the smallest amount. The smallest is for the carbon, 0.627. So if you divide 0.627 by 0.627, you get 1. So carbon will be 1. If you divide hydrogen by carbon, 1.25 divided by 0.627, you get about 2. And if you divide 0.626 for oxygen divided by 0.627 for carbon, you get you get 1. I'm sorry, you get 1, yes. So 1, 2, 1. So be careful. It doesn't have to be exact. 0.626 divided by 0.627 is not exactly 1, but it's very, very close. So you get 1, 2, 1. That would be the empirical formula. 1, 2, 1. Carbon, hydrogen 2, oxygen. 1, 2, 1. CH2O would be the empirical formula. And that's the final step in this particular problem, is how do you find the empirical formula? Now, there is one more step that we want to be able to do, and that is to find the molecular formula, which is the actual number of atoms in the chemical formula. Here's how you go about that. Determination of molecular formula. The empirical formula gives you only the ratio of combinations of atoms in the molecule, but there could be more than one molecule that has the same empirical formula. So here's how you go about it. We have to have one more number, and that is called the molar mass. If we have the molar mass of our compound, and it turns out the molar mass of glucose is around 180 grams. Now we can take the empirical formula and convert it into a molecular formula. Here's how they show you to do it. You have the empirical formula, CH2O. If you calculate what its mass would be, it's around 30 because carbon is 12, hydrogen is 1, but there's 2 of them, so that's 2, and oxygen is 16. So if you add up 12, 2, and 16, you get about 30. The molar mass is 180. That's given. Remember, that's not something you'd be able to figure out. It has to be given to you in the problem. So what you do is you say, look, if something weighs 180 and it's made up of little units that weigh 30, how many of those units are there? 180 divided by 30 is 6. So that means there's 6 empirical formulas for every one molecular formula. Think of it like a little train. If one car weighs 30 tons and the whole train weighs 180 tons, how many cars are there in the train? 180 divided by 36. So that means that the molecular formula has a mass that's 6 times that of the empirical formula. Well, the way you get that is you say it must have 6 times as many atoms. So if the empirical formula has 1 carbon atom, the molecular formula must have 6 times that. So that'd be 6 carbons. And if the empirical formula has 2 hydrogens, and the molecular formula has 6 times that, it must have 12 hydrogens. And oxygen, if the empirical formula has 1 oxygen atom and the molecular formula is 6 times that, it would have 6 atoms as well. So the molecular formula would then be C6H12O6, which is given at the end of this paragraph. So if you look at the structural formula here, it's for glucose, it's given. Remember, carbon is black, oxygen is red, hydrogen is white. Glucose has a very interesting structure. It's a ring structure. It has 6 atoms in a ring. 5 of them are carbon and 1 is oxygen. And then attached to those carbon atoms is another carbon or an oxygen. So there's your ring structure. Count them up. C6H12O6. The empirical formula would be CH2O. Okay? The sample problem is a similar problem. They're telling you pretty much the same information. It's a little simpler, though. In this case, they're doing benzene, and benzene doesn't have any oxygen in it. So you just need to find out how much carbon and hydrogen are in the sample in order to find its molecular formula. You don't have to worry about oxygen. It also has a ring structure with carbon in the center and hydrogens attached. Okay? Same methodology, setup and solution here. If you take a look, they're doing it exactly the same way they did the previous one. So practice that one. Here's another one. Practice problem A. Do the same thing. This one is vitamin C, so it does have oxygen in it. So there you've got 3 elements. And then you've got your checkpoint problems, which you can try as well. So it is probably so far the most involved type of problem that we've covered. It requires multiple steps, but notice it also requires that you be able to do the steps very quickly. that you learned in the previous section. So if you remember in the end of the last lecture, section 3.4, I said, look, you got to be able to do these calculations to be able to do future calculations, and this is really it right here. You get to see that. If you're trying to find the mass of carbon and the mass of hydrogen, and you can't calculate the molar masses of those compounds, it's going to be a problem. So make sure you're practicing the mass to mole conversions and the mole to mass conversions. Practice back and forth and from section 3.4, and then try these as well. This will give you more practice at doing those sorts of calculations. And then try as many of these practice problems and checkpoints as you can bear, and you'll get good at it pretty quickly, and that'll help you out for the future. Okay?